guys, welcome to chapter 13. In this chapter, we are going to be talking about chemical equilibria. For those of you that are in my online hybrid class, this chapter will serve as kind of the next two modules. Lots of information here, so we'll spread it over a couple of weeks. So here's our path through the chapter. So first, just introducing this idea of what equilibrium is. And then towards the end, we'll talk about calculations and then Le Chatelier's principle. So the first half is just going to be an introduction to equilibrium and then calculating a few pieces here and there. So chemical equilibria. We have actually talked about this or introduced it in other chapters, but here's where we're really going to get to know it. We're going to be best friends with it by the end, okay? So what we're looking at here is a reversible reaction. So that's probably the first piece that's new. Up until this point, we had been doing kind of one-sided reactions, one-sided arrows. So our reactant breaks down into our product, and it goes in one direction. That's it. Reaction over. But with reversible reactions, what we're going to see is the forward reaction will happen, but then at some point, the product will start to react with itself and push back towards the product. So we'll see this kind of forward reverse action happening. So reactions can be reverse reactions and are represented with equilibrium. Okay. So let's take a look at the following reaction and let's talk about what this might look like. So first, here is our reactant N2O4. In the picture I'm about to show, that reactant is colorless, so it does not have any color associated with it. Once that has reacted and becomes the product, that NO2, NO2 has a brown color to it. So that's one of the ways that we know that the product is being formed is the color is changing, it's turning brown. So let's look at this series of pictures here, okay? So in the first picture, we've got just the N2O4, just the reactant. So there's really no color to that. And there's only one direction for this to go in the beginning, right? So if we have all our reactant, no product, the only direction for this to flow is from reactant to product. So we start making the NO2. So as we start to make the NO2, that would be this next picture. So it's starting to get that brownish color because the amount of NO2 is increasing. Then we're going to reach a point where we've made the maximum amount of NO2 that we can. And what's going to happen is that's going to start reacting with itself. And it's going to push back to N2O4, back to the reactant side. So maybe in this second picture here, we had like 4 molecules becoming product, 1 slipping back to reactant. 4 becoming product, 1 slipping back to reactant. And that continues until we get to this third picture. And once we reach this third picture, we made kind of the maximum amount we can make. What we will see is the rate of the forward is going to be equal to the rate of the reverse. So we make 1 product, and then 1 product slips back to reactant. Make 1, 1 goes back. Make 1, 1 goes back. So we're going to see the rate of the forward equals the rate of the reverse. And then that's what we see in these last 2 pictures. While this is still a dynamic process, the reaction is still taking place. That color is not changing because the overall concentration or the overall amount is not changing. Rate of forward, rate of reverse is the same. Those are steady. So here's just words of the same thing that I just described. So when NO2 is placed in a closed container, reddish brown color starts to form as we're making that NO2 forward reaction. As NO2 builds up, it can react with itself and slip back into that reactant state, so going from product back to reactant. So we call that the reverse reaction. And then once equilibrium has been reached, the amounts of the reactants and the amounts of the products stop changing. It's dynamic. It's not that everything stops. It just means that the rate of the forward equals the rate of the reverse. Okay. So let's take a look at this dynamic process in kind of pictorial or graph form. In this first graph, so let's focus on this first graph down here at the bottom. In this first graph, we are, pull it in so we focus. In this first graph, let me talk about the units so we can see what we're dealing with here. So as we go from left to right, time ticks away. So we're just that reaction taking place, time equals 0, and then time ticks away. On the other axis, we have rate. So something that's down here would be 0 rate. It's not forming or not reacting. Something up here would be a very, very fast rate. It's forming or reacting at a high speed, or a lot are going away. So at time equals 0, we've got our N2O4 reactant. We've got absolutely none of our product. Okay, so as time ticks away, there's only one direction for the concentration of N2O4 to go, and the only direction is for that concentration to go down. Okay, so we see a fairly steep slope here. It's going to react at a very fast rate, and it's going to disappear because we're using it to make the product. On the other side, we see that we had absolutely none of our product. There's only one way for that to go, and that's for some to get created, okay? So again, we see this very steep slope. We're going to create the product, and we're going to create it at a pretty good clip in the beginning here. Okay. So we reach equilibrium. So this dotted line kind of represents that equilibrium. Once we reach equilibrium, what we will find is both of these lines converge, and the rate of the forward reaction is equal to the rate of the reverse. So making NO2, using up N2O4, so both of those processes are still happening, but they're happening at a constant rate, and that rate is equal. So that's just kind of giving you a mathematical representation of what's going on. Another graph over here, again, across the bottom, we've got time ticking away, so time equals 0, and then as it progresses. On the other axis here, we've got concentration, so we've got amount of our product and our reactant. So again, we see at time equals 0, we've got none of our product, we've got a lot of our reactant. There's only one direction for the reactant to go, and that's to go down. The concentration goes down, it gets used up. There's only one direction for the product to go, and that's to make some, right? We have 0, we got to make some. So we see before equilibrium is reached, we see that the concentration of the product goes up. Before equilibrium is reached, we see the concentration of the reactant go down. Once equilibrium has been reached, so again, this dotted line represents that, what we will see is the concentration of our product, the concentration of our reactant levels off. It becomes constant, right? So we are not making any more, we are not losing any more. The concentration after equilibrium has been reached, that concentration will remain the same no matter what, okay? Very common misconception, and we'll talk about this later. Notice that the concentrations are not equal. Once equilibrium has been reached, we have a lot more product and not as much reactant, and that's fine. They don't have to be the same amount, but they do have to level off here. So just some more words. Rate of the forward reaction equals the rate of the reverse. That's that first graph. And then at equilibrium, the amount of reactant and product stops changing. It levels off or flatlines. If you need just some more information about equilibria of what I'm saying isn't quite sinking in, the next 3 slides are here for you to read. So I'd either pause the video and read through these or pull up the lecture from Canvas and click through them. So the next thing we're going to talk about is what I alluded to, and that's common equilibrium misconceptions. So the first misconception is the amount of products and reactants are typically not equal to one another at equilibrium. So we saw in that graph, the red concentration was much higher, the blue concentration was much lower. So they're not necessarily, and rarely are they, equal at equilibrium. So usually there's more than one or the other. So although the amount of reactants and products remains constant during the equilibrium, it is still a dynamic process. It's not static. So once we hit equilibrium, it's not that like, oh, everything stops happening. We're still creating reactant, we're still creating product, but it's happening at an equal rate. So it's like 1 and 1 or 2 and 2. So it's dynamic in process, but equal in the rate. So one of the best analogies that I've seen for this, and I cannot take credit for it, it actually comes from your textbook, but one of the best analogies I've seen for this is two people juggling. Okay? So here we see two gentlemen that are juggling. They're juggling pins, right? So it looks like we've got 1, 2, 3, 4, 5, 6, 7, 8 pins, okay? So before they begin, let's pretend like this guy over here in the blue shorts had all 8 pins, okay? So he's going to start by throwing one to his partner. There's only one direction for those pins to go, and that's to his partner because he didn't have any. Then he's going to throw a second one. Then he's going to throw a third one, okay? At some point, this guy's hands are going to be full, and he's going to have to start throwing him back to the other guy, right? So that's our dynamic process. He throws one, he throws one. He throws two, he throws two, so on and so forth, okay? So once these two hit equilibrium, once they hit their flow of juggling, what are some things that we notice? We notice that the number of pins stays the same, right? So we're not losing any pins, we're not gaining any pins. We've got 8, and we're going to remain with 8 pins throughout, okay? We also notice that once they hit equilibrium, the number of pins that they are holding will also be constant. So that's what I said, the concentration of products, the concentration of reactants will be constant at equilibrium. So for these guys at equilibrium, he's going to be holding on to 2, he's going to be holding on to 2, and that won't change. Which pin they're holding will change, but the fact that they're holding 2 will not change. They will always be holding 2. So the concentration of pins in their hands will remain constant at equilibrium, okay? And then also we see that this is going to be a dynamic process, right? Even though this is a static picture, we can picture these guys juggling, right? The pins are constantly moving from one place to the other, okay? So just an example of equilibrium, just to give you kind of a qualitative idea. We're going to be talking about equilibrium for the entire chapter, so I wanted to make sure we had a good solid foundation as to what it was. I hope you guys found this helpful.